Folks, if you're not part of the solution, you're part of the precipitate. So the precipitate is that cloudy or fuzzy stuff. It's an So what happens if we take two ionic compounds, both in aqueous solution, clear solutions, and we mix them together and they form something new? Chemical reaction occurs. You've observed this. It suddenly gets cloudy, or it gets chunky, or stuff drops out of it. You've formed a precipitate. When you form a precipitate, what you've done is you've created a compound that's insoluble. And that's when you get a precipitate. Remember, we get bubbles when you get an insoluble gas. You get a precipitate when you get an insoluble solid out of a liquid solution. And we can actually predict if you're going to form a precipitate and what the precipitate will be. If you take a first year of general chemistry at most colleges, half to a third of that will involve a laboratory portion of quantitative analysis. And a lot of quantitative analysis is predicting products for reactions, running the reaction, getting precipitates, and then predicting what they are and testing them to see if you're right. So, okay, you can predict if a precipitate's going to form and what it will be. So, you got 2 slides of notes here. I break this down into a few more steps. So it's a lot of words. Just kind of bear with me. We'll talk through this one, and then we'll do an example together. So if we take a solution of ammonium sulfide and a solution of cadmium nitrate, and they're both in aqueous solution, which means really what we have is we've got one container that has a bunch of ammonium and sulfide ions floating around in it, and we've got one container that has a bunch of cadmium and nitrate ions floating around in it. That's really what we have. If we put those things together, will we get a precipitate? Will we get a solid product out of these two aqueous solutions? Well, we can predict what the products would be if a reaction happened, and then we can look up and see if cadmium sulfide is soluble. And if it's not, we're going to get a cadmium sulfide precipitate. Let's do this as an actual problem, step by step. Ammonium sulfide in aqueous solution is mixed with cadmium nitrate, also in aqueous solution. Write the net ionic equation. This is really how we get down to what happens, what actually reacts. And it's a multi-step process. First step in looking at this is writing a dissociation equation for each potential reactant, because you need to know what's actually in those solutions, how much of everything is in those solutions. So we had ammonium sulfide, whoops, and we take a solid ammonium sulfide, we dissolve it in water, we dissociate it. What do we get out? So we get out 2 moles of ammonium ions with a 1+ charge in aqueous solution, 1 mole of sulfide ions with a 2- charge also in aqueous solution. Does that make sense? Does that look right to you? Okay. The other thing that we have is the cadmium nitrate. Cadmium is Cd, right? Okay, so we also have the cadmium nitrate. 1 mole of cadmium nitrate solid. Associated in water, we get 1 mole of cadmium 2+ ions and 2 moles of nitrate 1- ions. Those are all in aqueous solution. So now we know what we actually have in aqueous solution, and we're going to kind of set that aside, because what we want to think about is what would happen if we forget what we're doing now, and we forget what we know, and we go way back to when we were just looking at chemical reactions and predicting products. What would happen if you put these two things together and you got a reaction to occur? So the second step is to write a double replacement reaction. And we say write a double replacement reaction for the possible reaction, because what we're actually doing here is figuring out if any reaction is going to occur. We don't know yet. We don't know. So what we're showing here is ammonium sulfide in aqueous solution mixed with cadmium nitrate in aqueous solution. And what would be our potential products if we do a double replacement reaction with these? Ammonium nitrate and cadmium sulfide. It does not matter which order you write them in. It does, however, matter that you balance the equation. And this one's pretty darned easy to balance. We just put a 2 there. Here's the other thing that really matters. We don't know the state information on these things yet. We have to go look it up. So I typically, in my first run through, just put a little question mark in the state information for the products. Now, we've done enough stuff just today. You probably remember that ammonium nitrate is incredibly soluble. It's a plant fertilizer. Plants use it because it's dissolved in water, and it's a good source of nitrogen for them because you get nitrogen not only from the ammonia, but from the nitrate. It's highly soluble. So we know almost immediately that this one, ammonium nitrate, is soluble. What you might remember from the chart, and if you've got your quiz handy, you can just look right at the chart that you've got out. Most sulfides are insoluble. And cadmium is not one of the exceptions to that rule. So cadmium sulfide in the product is going to be a solid. Well, what this means is that a reaction is going to occur. We're going to get a precipitate, and that precipitate is going to be cadmium sulfide. So we've now done our second step, right? A double replacement reaction for the possible reaction. So far, this is all old skills. This is a skill that you basically learned yesterday, you fipped on today, you did well with. Whoops. This is a skill that you've had since chapter 8, and mixed with a new skill, which is looking up solubilities and predicting them. So now we're going to put a few more things together. The next thing that you're going to do, step 3, is write an overall ionic equation. So we could also call this a gross ionic equation. Ew, get it? Haha, gross. This is everything in. This is all in. This is your whole paycheck. This is all of the ions that are reacting. But to write an ionic equation, we no longer just write this, which is all these compounds we're showing. We actually go all the way back to here, and we take these ions that we know, are floating around in aqueous solution, and we show them all together. And if you're using something like, well, you're not using Doceri because they took away your devices, but you can just write them. If you're using an electronic anything, then you can just copy them. So notice that we've got the correct numbers of moles of all of those ions because we borrowed these directly from the dissociation equations. And we can't just say, oh, yeah, 1 mole of ammonium ions, because when we dissociate that ammonium sulfide, we get 2 moles of ammonium out of it. So you have to keep those coefficients. Now, this is only half, of course, of the equation. Every equation has 2 sides. And what we get out of this is really the crux of the issue. So, does ammonium form a new solid, non-soluble compound on the other side of this equation? No. Ammonium's still just hanging out. Ammonium is so soluble, you cannot get it to hold hands with another ion when it's in water. So our ammonium ions come through unchanged. Is sulfide involved in a compound on the other side of this? And we have to go back to here and look at our state information. Yeah, cadmium and sulfur, cadmium and sulfide ions are going to form a compound. So we're actually going to write that. And then what else is left just sort of drifting around in the mists over here? Yeah, the nitrate ions. Just floating around, not really doing anything, just hanging out. So this is our overall ionic equation. And what it shows is all the ions that you threw into that soup of ions in the beginning. And once they're mixed together, it shows what they do. And what we're seeing is that the ammonium and the nitrate continue to be, dissociated out in solution, not forming a compound. But the cadmium and the sulfide ion actually form an insoluble compound. They're going to precipitate out. That's our overall ionic equation. There's a fourth step. You might have guessed that. And we can do this one right on here. Cancel spectators. Have any of you ever been a spectator at an event? I would imagine that you mostly all have. What's a spectator? Yeah, spectator just watches. Doesn't participate in whatever it is that you're doing, just watches. So if you take that analogy, are there any ions here that are not participating in a reaction? That don't form a new compound at the end? Yeah, nitrate's one of them. So the nitrate ion does nothing. It just hangs out. It just stays in solution. What else just stays in solution? What? Yeah, the ammonium. Those are your spectators. They just watch the action. They don't do a thing. Once you've canceled out your spectators, your final step is to, and I guess we should take this to the next page probably. The last step is to write your net ionic equation. So your net ionic equation means that those ions that didn't participate in any way, that were just spectators, you don't write. And so our net ionic equation for this is going to look like this. S2 minus aqueous plus CD2 plus, also aqueous, forms cadmium sulfide, a solid. That's it. That is our net ionic equation. So it's 5 steps. We're going to run through one more together, then I'm going to give you a bunch of practice, and I'm going to float around. I know, it seems overwhelming, doesn't it? Even though the first 3 steps are all things you know. We'll come back after the bell and do one together. Let's real quickly just look at the slides for this and see if these steps sound a little bit more comprehensible now that you've seen one done. So for a net ionic equation, you take the dissociation equations, you look at which ions are going to participate. You know that the ammonium and the nitrate, stand out, stay dissociated. Those are the spectator ions. They just stand there looking. They don't do anything. They're kind of useless in the general scheme of this equation, this reaction happening. So we cancel them out, and what we're left with is our net ionic equation. Because net ionic equations only show the ions that actually participate. So there's our net ionic equation. Okay. They're hard. The gross ionic equation, the overall, is hard to always fit on a line, but we'll do it. So let's do one more together, and then I'm going to give you practice. Okay, so will a precipitate form if aqueous solutions of barium chloride and sodium sulfate are mixed? If yes, we need to write a net ionic equation. What's our first step? Ooh, it's a chapter 7 skill. Right in the darn formulas. So we have barium chloride. Remember, barium is Ba, chloride is Cl. Barium typically forms a 2+ ion, so this is going to be BaCl2+, BaCl2. And sodium sulfate, Na2SO4. So step 1 is writing dissociation equations. Because we want to know what's actually going to be in that aqueous solution, in that soup. H2O, so we get Ba2+, aqueous, Cl1-, and we get 2 moles of chloride ions, also an aqueous solution. I'll let you do the sodium sulfate by yourself. Okay, so you have 2 dissociation equations that look like this. You should have your charges shown, you should show the state information, and you should show the proper number of moles. A couple words about writing your dissociation equations. If you've done everything right, everything balances. And by everything, I mean not only the number of atoms of each kind of element, but also the charges. So we have 1 barium here, 1 barium here, 2 chlorides there, 2 chlorides there. Great. This entire side is neutral. Is this side neutral? Yes, overall it is. Because you have 1 that's got a 2+ and you have 2 that have 1-. So if you've dissociated it correctly, not only will your atoms balance, but your charges will too. Okay. So moving on, what's our second step?